Okay, so Thursday you have to turn something in. And what you need to turn in is everything that says the problem's due 9/8. That doesn't, I guess one thing that I did that might be a little confusing is the first thing I'm writing on all these assignments is to read today's notes and work through the example problems. You don't have to turn that stuff in. The stuff you have to turn in is the problems that are listed here that are posted in D2L. So let's see, vectors 1 through 15. The 4 additional problems under more vector problems, and particle free body diagrams, particle kinematics 1 through 3, and then whatever I assign today. Okay, that's all. Oh, really?
Yeah, is that a PDF?
It should be. Oh, yeah. Yeah, it's not. Right, it should be particle statics. Sorry about that, I just wrote that wrong. I'm going to change that right now. Kinematics in statics would be pretty boring. Like you don't even have to know the problem. It's just like statics problem, derive the kinematics or whatever, like everything's 0. All right, this is more like it. And then I'm going to assign something for today, more particle statics. And then, so all that, staple it all together into one packet and turn it in. And I'm going to pick out, 2 problems, say, from the whole thing using a random number generator. I'm going to look to make sure that you've done all the problems. And then I'm going to grade those 2 problems I pick at random. And that's what the score for the homework assignment is going to be based on. Okay, yes?
Do we have time to ask questions on the problems that you assigned today before we hand it in?
That I assigned today?
Yeah.
I guess at office hours, that's the only way, or email. So I finished last time by writing up a problem that I'm going to go through today. Before I do that, anyone have any homework questions?
The one extra vector problem, number 1.
Okay.
I didn't really get
Anyone have it in front of them? That would be easier. Yeah. Thanks. Number 1? Okay. So number 1, extra vector problems. You have this funny shape thing, but that doesn't matter because you can figure out the locations of all the points. The origin is at the center of mass, which is marked with that circle with the X. So here's our coordinate system. What? Oh, yeah. The cable attaches to the body at the point 0.6, 0.4. And the length of that cable is half a meter. this angle is 45. It doesn't look like it, but what are you going to do? And the pin down here is at the point 0.05, negative 0.2. And the first question is, if the cable has a tension T, what's the force vector the cable applies to the body? So what's the force vector applied to the body by the cable if the cable tension is T? And then the second one, okay, well, the second one is the vector from the pin to the point where the cable connects to the wall. So I'll call this point W. I'll call this point P. And we want to figure out the vector to W from P. To figure out the force vector applied to the body by the cable, we know that tension is T, so we're going to multiply that tension T by a unit vector in this direction. So all we need is, the only thing we don't have is a unit vector pointing away from the body at 45 degrees from the horizontal. So for part A, that force applied to the body by the cable is equal to T times the cosine of 45, sine of 45. That's 0.7071, so this just gives you 0.7071 T, 0.7071 T. Any questions about the first part? And then the second part, we want to figure out a vector that goes from P to W. So we're trying to figure out.
I have a question.
Yep, sure.
Is there a reason why you didn't use the 0.5 meters in your?
We're going to use it in the second part, but what we wanted to do was the only reason that cable was useful at all in part A was we know that the force applied by the cable is parallel to the cable, pointed away from the body. So we know that we want a unit vector that's parallel to that cable, pointed away from the body. And so that half doesn't come into calculating a unit vector. That could have been any length. And what you could have done, I mean, the long way around, where if you wouldn't have seen that from the start, you could have said, okay, the vector from here to here is 0.5 times cosine and sine of 30, and then take the unit vector of that, and you realize, oh, I just divided that 0.5 back out, you know. Okay, well, so that works fine too. Okay, so for part B, we want this blue vector. So we have the coordinates for P. We need the coordinates for W. So the coordinates for W, I'll write it like that, are equal to 0.5 so 0.5 times cosine and sine of 45 degrees plus the coordinates of this point, 0.6, 0.4. Okay, let me draw what's going on there. So if we're trying to come up with the coordinates of W, okay, that's the orange vector. The way we're going to do that is we're going to add a vector that goes from the origin to here to a vector that goes from here to the wall. The vector that goes from the origin to this point is already given. That's 0.6, 0.4. And so now we just need to figure out that remaining black vector. I guess I'll write that as, draw that as purple too. And then we're just going to add those two together. It's just vector addition. So this is 0.3535, 0.3535 plus 0.6, 0.4 is 0.9535, 0.7535. Yep.
Would you have to have a distance from P to the origin too?
From P to the origin, we already have that given as coordinates, so we don't have to figure that out. The only vector that we need to figure out the components for is that second purple vector that goes from the attachment point to the wall. All the other ones are given, and we can just add those. So then the vector that we want, U, is equal to, we want the one going to the wall, right? Yeah. So we want W minus P. So that's 0.9535, 0.7535 minus 0.05, negative 0.2, and that's 0.9035, 0.9535, I think. Any other questions about that one? So when you're given coordinates of a point, you can always think of that as a vector going from the origin to that point, and you can always use that accordingly in vector calculations. That's what we did here. Yep.
Wouldn't those both be negative because it's from W to P?
From W to P. I subtracted both of these. But this one, the y coordinate was negative, so that ends up being a double negative, so you end up adding it.
I'm just thinking like geometrically
Yeah.
it's pointed towards like the third quadrant.
We're trying to represent this blue vector. And so that blue vector is in the first quadrant. We're trying to calculate the vector that goes from P to W.
My bad.
Okay. I mean, this is let's try to straighten as much of this stuff out now as possible, because I think every minute we spend doing this will help later.
Yeah, I just had the 2 points flipped.
Okay. Yeah. Right. Any other questions about this one? Yes.
No, there's one more.
Okay. Well, any other questions about this one before I go on? Yeah.
I just have a question in general. So if you're just as a naming convention, if you're talking about the vector from point A to point B, would you suggest, like, if
I think I tend to do it
AB with a
2B from A,
okay.
the same as the force. That's how I tend to do it. But I don't think there's any convention for that, really.
I'm just wondering if I have to like write it each time. Like,
You don't have to write, you never have to write that, but,
Yeah, just
so you can just, yeah. I mean, I can figure it out from the context. Any other questions? Okay, yes.
Well, it's just the way the questions were. It said vector to W from P. So what you were saying is probably from. Why don't you subtract the P? From the W?
You're always taking the destination point and subtracting the starting point. So this is going to the point where the cable connects. So the destination point is W at the wall, and minus the starting point, P. Guillermo, you have a question? Mm-hmm. Okay. Okay. Well, okay. This one is pretty hard to draw. Let's see. Why don't I insert it here? Thanks. Okay, well, let me just do it on the, let's look at it up here. All right, so we have the x-axis going this way. Oh, no, we don't. Okay. Start over again. We have the x-axis going this way. And the y-axis, so that axis, you know, comes all the way back to there. That's the origin. The y-axis going this way. And so the z-axis is going this way. And for each one of these points, I think the easiest way to do it is just start out by figuring out the coordinates of all these points, and then you can do the subtractions. Oh, okay. Okay. So let's just figure out a couple of these since we're here. What? Okay. So the coordinates of h. H is just, so if this is the origin at D, to get to h, you just go a total of 100 inches in the negative z direction. So the coordinates here are 0, 0, negative 100. This is in inches. for that point I, to get there, you're just going from the origin 44.8 inches in the positive y direction. So 0, 44.8, 0. Any questions about either of those? G is just in the positive z direction, a total of, well, I covered it up, but I think that says 136 inches. So that's 0, 0, 136. Let's do, so these are all just going along a single axis, but now we have to do a couple where you're going along multiple axes. So let's say the point F. To get to F, you travel from the origin along the positive x-axis until you get to B. And then from B, you have to go 10 inches in the negative z direction to get there. So this point F would be 120 in the positive x direction, 0 in the y direction, and then negative 10 in the z direction. Yep. What? The one, where did I get that from? This dimension right here. So that says you have to go 120 inches in that direction to get to the center of that pipe. And then you have to go 10 inches in that direction to get to F. And so in these three-dimensional problems, that's how it's always pretty much going to be given. It's going to give you ways to figure out, you can go this way along the x-axis, this way along the negative y-axis, and then this way along the negative z-axis, and those are your three components. Any other questions about that one? Oh, we're not done yet. Once you get those coordinates, then you just have to subtract the vectors to get the vector going from one to the other one. So like the vector from, what do I have? The vector from G to I would be 0, 44.80 minus 0, 0, 136. So it would be 0, 44.8, negative 136. And what that would give you is the vector that vector. Any other questions on that set of problems, those extra vector problems?
From E to C.
From E to C. Yeah, so C is, to get to C, you just have to go 72 inches in the positive x direction. So 72, 0, 0 is C. E, you have to go 120 in the positive x, and then positive 10 in the z. So E is 120, 0, positive 10. And so E to C is this vector. And it's just 72, 0, 0 minus 120, 0, 10, which is minus 48, 0, minus 10. Okay? All right. So I was going to do an example problem where we had a ramp at 40 degrees and I can't remember, were there wheels on one of these two boxes?
Bottom one.
Okay, so there's a 3 kilogram box like that, and then a 2 kilogram box like that. And the cable's attached to the 3 kilogram. And this is attached to the ground down there. And we want to figure out, I don't remember what order I said before, but let's say the force the cable applies to the 3 kilogram box. The force, the incline, applies to the 3 kilogram box. And the force, let's say the 3 kilogram applies to the 2 kilogram. We're going to have to isolate two bodies. You kind of have a choice. You could isolate the two of them together, or you could isolate the two of them together and then isolate one of the individual ones, or the two individual ones. But either way, you're going to have to use Newton's second law twice. Let's just isolate the two boxes. So free body diagram of the 2 kilogram box. So there's the outline. Then there's the weight force of 2 times 9.81. And then this is a friction contact. So the only place that the outside world makes contact with the 2 kilogram box is here. That's the force on 2 by 3. And Newton's second law says 0, negative 19.62 plus F23x, F23y is equal to zeros, because there's no acceleration. And so the force on 2 by 3 as a vector is 0 for an x component and positive 19.62 for a y component. And actually, that's already part C. And then we'll isolate the 3 kilogram. There's the outline. There's the weight of 3 times 9.81, so 29.43. And now we're just going around the boundary looking for contact. I'll start at the wheels. What do we know about the nature of the contact between the wheels and the ground? It's frictionless, so that's a pushing contact. So it's perpendicular to the surface toward the chosen body, or it's just a normal force, and like you've done before. I'll just call that N. And keep going around counterclockwise. We get to the contact between the body and the cable. What do we know about the nature of that contact? Yep, parallel to the cable, away from the body, so like that. And then we get to the top. The top touches the 2 kilogram box. What do we know about the nature of that? Yeah, that's right. That's the force on 2 by 3, which is negative F32. Actually, no. What I wrote here is wrong. This is the force on 3 by 2. It's negative F23. And so, and we already calculated F23, so this is equal to 0, negative 19.62.
Why is the force is pushing up if the force on 3 by 2, why is it going up instead of going downward?
Why did I draw it like that?
Yes.
I just drew that to say, when I draw it like that, all I'm saying is, this is, the sign convention says a positive x component means that way, and a positive y component means that way. And then the value of the y component is negative, which means that really that force is acting down.
Yes.
So that's just showing a sign convention.
Oh, okay.
Okay, but that's important because if you instead drew this as going down,
Yeah.
and then wrote this is 19.62, that would be saying you have a unit vector down times a constant of negative, which would be a double negative, and you'd really be saying the opposite of what you mean.
Oh,
So if your forces go in as vectors, you always need your unit directions to be in the directions of the axes.
oh,
Okay. So don't when you know the directions of those components, don't use that to adjust the directions of those axes. Okay. Okay, so this is negative F23, which comes from over here. And that's all the forces acting on body 3. So Newton's second law says 0, negative 19.62 plus 0, negative 29.43 plus, now we have to do some stuff with unit vectors. So what do we know about these directions? Well, this one is probably the easier one to see. This is just an angle of 40 degrees. So this force is going to be a magnitude of t times cosine and sine of 40, which is 0.766 t, 0.643 t.
So cosine 40 t.
Yep, that's right. This is t times cosine of 40, sine of 40. And now we have to figure out the angle for n. So I think the easiest way to do that is to think of n as just being perpendicular to t. Okay, so I'm going to just take the tail of this vector n tail of this one, and then imagine my coordinate system in there like that. So we go plus 40 to get to t, and then we go another plus 90 to get to n. So 40 plus 90, 130. And so this is going to be n times cosine of 130, which is negative 0.643 n, positive 0.766 n. Okay, and this one comes from n times cosine and sine of 130. And that's everything. So this gives you two equations. The first one says 0.766 t minus 0.643 n is equal to 0. And the second one says 0.643 t plus 0.766 n is equal to, what's that, 4... If you add those two together. Oh, yeah, right. 49.05. Okay, so that's a system of equations we need to solve. So how do we solve that system? Well, that's a small system. It's two equations for two variables. There's a million ways you could do it, substitution or whatever. But systems of equations are going to be a big thing in this class, and sometimes the systems are going to be as big as 20 by 20 or so. And if you have 20 by 20, then substitution is kind of out of the question. You're just not going to do that. So the way to do this, so we're going to solve this system using reduced row echelon form. You either have taken a class where you had to learn how this works, or you will take a class where you had to learn how this works. Me too, but I have no idea anymore how it works. I just plug it into a calculator, and that's all you have to do in this class. So the way to do that is, first, get all variables on one side of the equation and all constants on the other side. And I did that. Second, write in the form of a matrix with n rows, n being the number of equations, and n plus 1 columns. And so in our case, it's going to look like this. Okay, so we have a system of two equations and two variables. So our first equation is this row. Our second equation is this row. And then our columns represent the variables. So our first one is going to represent t. Our second one is going to represent n. And then our third one is going to represent the constants. And now we're just going to go through those equations and write down the coefficient for in the appropriate box for each of those variables. So what's the coefficient for t in equation 1? Yep, so 0.766 for n. Yep, negative 0.643. The constant, 0. For equation 2, the coefficient for t, 0.643. For n, 0.766. The constant, yep, 49.05. Your different calculators have different ways of entering this matrix, but so if you can't remember how to do that, figure out how to do it, come talk to me and we'll get it programmed in. But once you have that programmed in, you're just going to run the function. So let's say that you call this matrix M. Okay? So now you're going to run the function RREF on M. And it is going to give you a matrix out that is the identity matrix in the first two elements of each row. And then the third row is going to give you, the third column is going to give you the answers in the order that you have the variables. So this answer is going to be, that's the answer for t. This one's going to be the answer for n. Can someone punch that in and give me those two values? Yes? Okay. 37.57? Okay. So that's your answer for t. That's your answer for n. It didn't save really any time to do it that way for two variables, but when we get to 4 or more, it'll save you a lot of time. And when we get to 20, it'll save you a day. Okay, well, we solved the system, but we haven't actually answered the question yet. The question asked for the force, so meaning the force vector the cable applies to the 3 kilogram cart. So how are we going to get that? Well, this vector here in Newton's second law is the force vector applied to 3 by the cable. And this vector is the force on 3 by the incline. So all we have to do now that we know the values for t and n is plug them back into these vectors, and it'll give us those force vectors. So the force on 3 by the cable is equal to 0.766 t, 0.643 t. Can someone multiply 31.53 times 0.766, 0.643? 24.152? Okay.
And then 20.273.
Okay. So that's the force vector applied to 3 by the cable. And then for the normal, the force on 3 by the incline, that was equal to negative 0.643 n, positive 0.766 n, right? I think so. Yes. And so now multiply that unit vector by n, and what do you get for that one?
Negative 24.16
Okay.
and 28.78.
Okay, so if this problem had asked for the cable tension, you just give that value T. If it asks for the force, it should specify. If it asks for the force vector applied to 3 by the cable, then you have to plug that tension back in to the force vector to come up with, to get the components. Same thing with the normal force. If it had just asked for the magnitude of the normal force, then the answer would have been n. But if it asks for the force vector, you have to plug it back in. What's the force applied to the cable by box 3? Yeah, the negative of that, because it's Newton's third law. So it would be negative 24.15, negative 20.27. And what's the force on the incline by box 3? If you work for an incline company and you're trying to figure out if your incline's going to break, you need to use the higher quality wicker or whatever on your incline. Again, you just take the negative because it's Newton's third law. So the force on the incline by 3 would be positive 24.16, negative 28.78. Any questions about that?
So here, F3 cable is the force
On 3 by the cable.
on 3 by the cable?
Yep. So now I'm going to do another example. This one's pretty similar to something you had to do, or you'll have to do in your homework. This one has to do with pulley advantage. I don't know, probably some of you, this was mentioned in Physics 1, and some of you it wasn't. But I'm sure everyone here has heard that pulleys are one of the, I don't remember the number, but the like super great machines. I can't remember basically. Simple machines. So you can use pulleys to decrease the amount of force it takes to lift something. You've probably heard that before. But then that sort of, I remember when the first time I saw calculations with pulleys, I was sort of confused because it's like the pulley doesn't actually reduce the amount of force required to lift something. It just changes the direction of the cable force, right? That's all a pulley does, just change the direction of the cable force. But it turns out that if you use a certain configuration, you can get this pulley advantage effect. And so I just want to show how that works. So let's say that we have, so here's the ceiling, and we have a pulley attached to the ceiling. And then we have, you can think of it as like a hanging pulley that's attached to a mass. So 100 kilograms. And the system is held together by a single cable that attaches to the ceiling here, goes over this pulley, then over this pulley, and then back down there. The idea is these should all be vertical. What's the force F that's required to keep this mass at rest. Well, if we didn't have this hanging pulley here, I should have drawn this. I should have done it the simple way first. But imagine that this 100-kilogram pulley was just attached to, so all this was gone, and you just had the 100-kilogram mass attached to a cable that went over that pulley. Okay? Just the simplest configuration you could have with that pulley. And you had to apply a force F to lift this thing up. That has a weight of 981 newtons. And that force F would have to be 981 newtons down to hold that up. Okay. That
Should be negative, right?
Yeah, well, the direction is given by the arrow. So I'm going to do this. Okay, so first, let's say we just have this 100-kilogram mass and one pulley and a force F. What's the F required for equilibrium? A free body diagram of the mass. Has 100 times 9.81 acting down. That's the weight. And then because this cable is weightless and this pulley is massless and frictionless, we have an upward force of F. And then Newton's second law, we'll use that to calculate F. So 0 F, because it's in the positive y direction, plus 0 negative 981 is equal to zeros, and F is equal to 981. So we had to apply a force that was equal to the weight. So now let's go back to this one. And what I'm going to isolate is the mass and the hanging pulley, everything that's hanging. So a free body diagram looks like this. There's the pulley. There's the mass. So what forces are acting? There's a downward force of 981. Yeah, and now there's, so drive around the boundary until you get to contact. And the first place you get contact is here. Okay? If you think this looks ridiculous, you don't have to do it, but I think sometimes on complicated cable problems, it helps to just include a little tiny bit of the cable in your isolated body, and then the direction of the force is always right out of the little stump of cable, you know? So we have a force T there. And now keep going around and you get to the other place where the cable contacts the pulley. So I'll include a little stump of cable over there. And since it's the same cable that's just going over massless, frictionless pulleys, that has to be the same cable tension. And so Newton's second law says 0, negative 981 plus 0t plus 0t again is equal to 0. And so this time you get that 2t is equal to 981. And so t, I've been, what did I call this one? I'm sorry, change these to F. We already named that F. So F on each of those, F in Newton's second law on each of those vectors. And so F is equal to 490.5. And that's pulley advantage. You can lift a 981 Newton force by only applying 490.5 newtons. And I think probably, like, if you're like me the first time you see this, your first thought is that it looks like sort of a trick or whatever, like find the place where I did something I'm not allowed to do or whatever. But it's not. That's actually how it works. And if you ever come to office hours in 1324, like on Monday or Wednesday, we can rig up a pulley and you can see how it works. You can feel the weight go down that's required because you're using 2 times the cable tension to lift this. Yep.
Would you still have the same effect, although to a lesser effect, if that hanging pulley had mass?
Yes, you would. Yeah, just depending how much mass and how much friction. You're right that friction, weight of the cable, mass of the pulley, those all just diminish it, and eventually you get to a point where if those are high enough, you don't get any advantage. So now, how about this? So now we have this pulley attached to the ceiling. That's a hanging pulley. Then we have another pulley attached to the ceiling. Another hanging pulley. Another pulley attached to the ceiling. One more hanging pulley. And these 3 hanging pulleys share the weight of, say 100 kilogram mass. And a cable strings through like this. What's F for equilibrium? So this time, we're going to isolate, again, just isolate everything that's hanging. And so the free body diagram. Looks like this. We have the weight of 981. Each pulley contacts the outside world in 2 places. And so Newton's second law says, I'm not going to do that. Let me do it carefully. So 0F plus 0F plus 0F plus 0F. 2 more times. 0F, 0F plus 0, negative 981 is equal to zeros. And so you get that F is equal to 981 divided by 6. And what's that? 163 point what? 5. And anywhere they have to move big shipping crates around, they use this idea. The pulleys aren't laid out in this way. They're laid out in a way that saves space, but this is the principle behind it. Block and tackle systems. And I want to do one more thing. Yes?
So 1/6 of the force is used by the person pulling the cable to hold it upright. That means 5/6 of the force
Yeah.
is coming from the ceiling.
That's right. Yep. And if it occurs to you that this seems like it might violate conservation of energy in some way, the thing that keeps it from violating conservation of energy is that in order to lift the, like in this last example, we have this really small force to hold up a big weight, right? But if you wanted to lift that 100 kilogram mass up a foot, you'd have to pull that cable through the pulleys 6 feet. And in this case, in order to lift that mass 1 foot, you'd have to pull the rope 2 feet down. Okay, so let me do one more example. So the idea of this is this all depends on the angle of the angles made by the cable. So let's do this again. So this time, let's say we have so there's the hanging cable attached to a 100 kilogram mass. And that's the pulley attached to the ceiling. But this time we have these very horizontal cables. let's say all these angles are 10 degrees. And we want to calculate F for equilibrium. I'm going to draw a free body diagram of the same thing as before, everything that's hanging. So we have the weight acting down, 981. And now we have force vectors. Those are always parallel to the cable. So we have one that way and one that way. And so Newton's second law says we have F times cosine and sine of, what's the angle representing this direction? From 170, yep. And this one? 10, yep. So we have F times the cosine and sine of 170 plus F times the cosine and sine of 10 plus 0, negative 981 is equal to zeros. That is negative point, I think it's 985 F, and then positive 0.174 F. I think I remember those. For 10, same thing, but positive 0.985 F, positive 0.174 F, plus 0, negative 981 is equal to zeros. The x components cancel, so you get one equation that says 0 equals 0. That doesn't do you any good. But the second equation says, what's that, 0.348? 0.348 F is equal to 981. And so what do you get for F? 2818.97. Okay. The 0.348? I added up, I have two times that I have 0.174 F, so I just added those up.
Well, yeah, but did the force increase?
Yeah, so no advantage at all. In fact, things got worse with that system. And that all happened because of this angle, because the component of the force vector in the vertical direction was very small. And as that vertical component gets smaller, your advantage gets worse and worse. And it actually approaches infinity. It never stops getting worse. So if you imagine the cable tension as this angle approaches 0 degrees, as it approaches perfectly horizontal, that cable tension is going to infinity. So so if you ever have to rig up a system like this and you think, like, I'm going to save some space by making the cable more horizontal or whatever, that's not good. That won't happen. Any other questions about that?
So if we go farther to go from the y direction, I mean smaller and stuff y direction, force will be like increased.
Right, exactly. Yep.
Plus,
Yeah. Okay. Well, that's the end of particle statics. I'll go put up the problems for today. I think it's just going to be the rest of the problems from particle statics, but I'll look them over and make sure that works. And then those problems are due on Thursday, and then on Thursday we'll start with the new topic, which is rigid body statics. Yes.